In this video, we're going to look at our last confidence interval for week 4, where we're constructing confidence intervals for proportions. And remember that proportions are percentages, and we typically talk about proportions when we talk about situations that are binomial in nature, meaning situations where there's only 2 outcomes. I'm interviewing people and asking them a yes or no question. I'm asking people something that only has 2 categories, or something that can be reduced to 2 categories. The layout of this process is very similar to the step list we've been using for estimations for means, with one extra step. Because proportions and the binomial distribution are not continuous, I need to check that the conditions for approximating a binomial with a normal distribution have been met before I start doing the plug and jug for my confidence interval. Because if those conditions aren't met, this confidence interval will not be a good estimate for the proportion that I'm trying to estimate. So let's go ahead and go through this checklist. So first, we define the proportion in words like we have been doing. Next, we're going to identify information given in the problem. And typically they're going to give you 2 to 3 pieces of this information. They won't give all of it to you. Most common, you'll be given X, which is the number of successes that occurred, and you'll be given N, which we know is our sample size. Sometimes you will alternately be given the P prime, which is the proportion of successes in the sample. Ooh, that is not how you spell proportions, Mr. J. And you'll be given P prime along with your sample size N. Ultimately, you will need 4 values, which is proportion of successes in the sample, proportion of failures in the sample, number of successes in the sample, and a sample size. We need all 4 of those values to do this calculation. Quick reminder that we know that the proportion of successes is equal to the number of successes divided by the sample size, so we can convert back and forth between the two, and that the proportion of failures is equal to 1 minus the proportion of successes. So that's going to help us for step 2. Step 3, we're going to check that the conditions for approximating the binomial with a normal have been met. And there are 2 things we need to check. We want to check that N times P prime is greater than or equal to 5, and N times Q prime is greater than or equal to 5. And I'm going to note here that this condition will vary depending on which book you look at. You're always checking at N times P and N times Q. In other words, we're looking at the number of successes and the number of failures in our sample. But some textbooks have a more rigorous check in ensuring that this normal condition have been met. And sometimes they'll check that this number is greater than or equal to 10 instead of 5. We're going to stick with 5 because that is most common for introductory statistics. It is important that you do this check because sometimes, oops, sorry about that, you will be given a problem where that condition is not met. And if that is the case, you should say, I cannot perform this inference. Assuming that you have passed the checks in step 3, it picks up with a normal confidence interval. Draw the distribution, find the critical value, do the plug and chug with the confidence interval formula, state your answer in a complete sentence. Reminders, we're using the standard normal distribution again. We're approximating the binomial with the normal, so this is going to be an inverse norm command on your calculator in order to get your critical value. The formula for the confidence interval is very similar. It is the population parameter that we are estimating, and we're using the best point estimate we have for it, which is the sample proportion, plus or minus our critical value times our standard error. And in a previous video that we saw that for standard error for a confidence interval where I only have sample data is p prime times q prime over n, and then all under a square root. Let's go ahead and run through this process in a couple examples to get some practice with it. So first example says, suppose 250 randomly selected people are surveyed to determine if they own a tablet. Of the 250 people surveyed, 98 reported owning a tablet. Using a 95% confidence level, compute a confidence interval estimate for the true proportion of people who own tablets. So in that last sentence, I'm told what I'm doing. Confident interval estimate for the true proportion of people who own tablets. I'm also given a confidence level for that confidence interval. I'm then given a random sample of 250 people. I'm given my sample size. And then out of those 250 people, 98 reported owning a tablet. That's the number of successes. 98 people is a number of successes. So let's go ahead and define our variable of interest and list those numbers. The words are hard today. So we are looking for the true proportion of people who own tablets. They were nice enough to give that to us in the last sentence of the problem. I'm then given a bunch of information. I know my sample size is 250. I know that the number of successes in my sample was 98. That's how many own tablets. My confidence level is 95%, or 0.95. Going back to step 2, I know I need to calculate p prime and q prime, and then I need to do a check. So we'll start with p prime and q prime. P prime is x over n. So 98 divided by 250, which is 0.392. And then I need q prime, which is 1 minus p prime, the probability of failure. And that gives us 0.608. Next, I need to check, is n times p prime greater than or equal to 5, and is n times q prime greater than or equal to 5. So 250 times 0.392 and 250 times 0.608. And I already know that 250 times 0.392 is just going to spit out 98. That is my number of successes. And then 250 times 0.608 should give me the number of failures, which is 152. Both of those are greater than or equal to 5. So I have met the conditions to do a z interval for a proportion. going to start by finding my critical value. So we're back to the normal distribution. I know 95% is about 2 standard deviations away from the center, but we're going to use inverse norm to check. I know inverse norm is going to ask me for an area, a mean, a standard deviation, and a tail. I know the area is 0.95 for standard normal, mean and standard deviation are 0 and 1, and then I want my tail to be a center tail, which is not a tail at all, but that's the notation the calculator uses. So second vars inverse normal. And we get 1.96 rounded. So our critical value is 1.96, just a little bit under inside of 2 standard deviations from the mean. Last thing we're going to do, we're going to calculate, oops, sorry about that, our confidence interval. So P prime plus or minus critical value times standard error for a proportion, P prime Q prime over N. So P prime is 0.392 plus or minus 1.96 times square root of 0.392 times 0.608, all divided by our sample size, which is 250. And I get 0.331 for the lower end. And 0.453 for the upper end. So looking back up at the top, based on our sample data, we can be 95% confident that the true proportion of people who own tablets is between about 33.1% and 45.3%. Let's go ahead and try one more. The next one says, a survey of 100 Americans found that 68% said they find it hard to buy holiday gifts that convey their true feelings. Find the 90% confidence interval for the population proportion. So I see 3 numbers, 100, 68, 90. The 90 is tied to find a confidence interval, so that must be my confidence level. The 100 is tied to a survey of 100 Americans. That sounds like a sample size. So the 68% must be my proportion, my sample proportion. And in this case, it is a sample proportion of people who find it hard to buy holiday gifts that convey their true feelings. So we'll go ahead and start our confidence interval process. We are looking for the proportion of Americans who find it hard to buy holiday gifts. That that convey their true feelings. We'll list what we were given. So we were given a sample size of 100. We were given a proportion of successes, which is 68% or 0.68. And we were given a confidence level, which is 90% or 0.90. I'm going to take these two numbers and I'm going to calculate the things I'm missing. I'm missing a Q prime and I'm missing a number of successes. So for Q prime, I know that's 1 minus P prime, and 1 minus 0.68 is going to be 0.32, assuming I can do math in my head. And I know that if P prime is equal to x over n, in order to solve for x, I'm going to multiply both sides of that equation by n, so I get that x is n times P prime. So n times P prime, I know n is 100 and P prime is 0.68, so that's just going to be 68. You'll also notice that's one of the two checks that I need to do. N times P prime is greater than 5, so we've met that check for normality. I also should do n times Q prime, which would be 100 times 0.32, which is 32, which is also bigger than or equal to 5. So we've met the conditions for approximating a binomial with a normal curve. So I can build a z-interval for this proportion. We start with our critical value, so we draw the normal curve. I know that 90 is going to be a little bit inside of that 2 standard deviation marker, because 2 standard deviations is about 95. So my critical values are sitting about here, and this area inside is about 0.9. We're going to go ahead and use inverse norm for this since it's the normal distribution. Our area is 0.9. Because it's standard normal, mean is 0, standard deviation is 1, and we're going to use our tail as center. Our area is symmetric and in the center. And we get 1.645. This is that special case that we typically round to 3 decimal places instead of 2 for a z. And now it's just plug and chug. So for a proportion, our confidence interval is P prime plus or minus our critical value times our standard error for a proportion, which is P prime times Q prime over n. So 0.68 plus or minus 1.645 times the square root of 0.68 times 0.32 all over our sample size of 100. So for our lower bound, we get a proportion of 0.603. And then changing the subtraction to addition, we get an upper bound of 0.757. So scrolling back up, we can say that we are 90% confident that the true proportion of Americans who find it hard to buy holiday gifts that convey their true feelings is somewhere between 60.3 and 75.7%. All right, if you have any questions on what you saw in this video, feel free to send me an email or drop by office hours. Otherwise, I'll see you in our next video.